So now we take the example of Sn. If Sn is n surds n 7 raised to the power n plus 9 raised to the power n plus 11 raised to the power n, then so that the limit Sn is 11. So how to solve this example? So we use the sandwich theorem. And how to use the sandwich theorem? We know that (11 की power n is less than 7 की power n plus 9 की power n plus 11 की power n, because we know that there are three terms and addition is greater than 11 की power n, because for all n belongs to n is natural number, and this number is less than equal to 11 की power n plus 11 की power n plus 11 की power n by the inequality. Then we can write this term, take n, eliminating n, so this is surd n 7 की power n plus 9 की power n plus 11 की power n, and this is 3 11 की power n इसकी whole power 1 by n. So here we take just like this is Sn. So 11 is less than, this is Sn, in less than, because the sandwich theorem says that it is less than or equal. Okay, so this is less than and equal, and this is 3 raised to the power 1 by n and 11 की power 1 से n cancel 11. So we take 11 is just like suppose Tn is just like 11, and Sn is Sn is that, and this is Un. Suppose Un is 11 into 3 raised to the power 1 by n, and taking limit, find the limit Tn. So limit Tn is limit n tending to infinite, and Tn is 11, so that is 11, and calculate limit Un, and limit Un is limit n tending to infinite 11 into 3 raised to the power 1 by n, and when we substitute 1 upon n taking limit, so this is 11 into 3 raised to the power 0, 1 upon n is 1 upon infinite is 0, and that is goes to 11. So limit Un, so here limit Tn is equal to limit Un, and which is equal to 11 by the sandwich theorem, and it is the positivity theorem by the sandwich theorem. First condition is satisfied, Tn is less than Sn is less than Un. Then second condition, both limit are equal, limit Tn is equal to limit Un is also 11. Then we can say limit Sn is also 11. So that is the result of this example, limit Sn is 11. Now we go for the another example for the sandwich theorem. We take the another example. Suppose we take Sn is at the form of n square plus 1 plus 1 upon n square plus 2 plus and so on 1 upon n square plus n, and find Sn, limit Sn. Find limit Sn. How to calculate limit Sn? So we know that solution. We know that the sum inequality condition 1 upon n square plus n is less than 1 upon n square plus n, because that term is smaller than this, and In the opposite side, we can, it is greater than this. 1 upon n square plus 1 is greater than 1 upon n square plus n. Similarly, 1 upon n square plus n is less than or n square plus 2, and so on, same thing. And the same condition, okay, 1 upon n square plus 2 is less than 1 upon n square plus 1, and 1 upon n square plus 3 is also less than 1 upon n square plus n, 1, and same. And we use this here, then we can write 1 upon n square plus n plus 1 upon n square plus n plus and so on, because it contains n terms. 1 upon n square plus n is less than equal 1 upon n square plus 1 plus 1 upon n square plus 2, adding this, and 1 upon n square plus n, and less than this condition, 1 upon n square plus 1 plus 1 upon n square plus 1 plus and so on, 1 upon n square plus 1. So this is the condition of inequality. By the condition of inequality, we can write this. And adding these terms, because the number of terms is n, so we can write n upon n square plus n. And here, this is what is Sn from first inequality, from first equation first. We can say this is Sn, and this is less than equal to 1, 2, 3 up to n upon n square plus n. So here we can say this is just like Tn, and this is Sn, and this is Un. So where Tn is n upon n square plus n, and Sun is n upon n square plus 1, because n square 1 upon n square plus 1, n square plus 1, and we can add, so this is 1, 2, 3 up to n upon n square plus 1. Now taking limit, so calculate limit Tn. What is the value of limit Tn? Limit n tending to infinite, n upon n square plus n, and taking n square is common. So here this is 1 plus 1 upon n, and cancel 1. N infinite, 1 upon infinite is 0, and that is 0 upon 1 plus 0. So that result is goes to 0. Okay. Now calculate limit Un. So what is the value of limit Un? Limit Un, so limit n tending to infinite, and what is Un? Un is n upon n square plus 1. Put n tending to infinite, it is infinite upon infinite form, so n tending to infinite. N square is common, so this is 1 plus 1 upon n square. Taking limit, so after n say n cancel, this is 1 upon infinite is 0, so this is 0 upon 1 plus 0, and that is goes to also 0. So it is clear that limit Tn is equal to limit Un, and both are 0. So by the sandwich theorem, we can write the condition is satisfied from the first condition, Tn is less than Sn is less than Un, and a limit Tn is equal to limit Un, and both are 0, then we can say limit Sn is also 0. So it is clear the result of limit Sn is 0. Now we go for the another theorems of sequence. So we take the sum, another theorems, another result. Next theorem, next result, theorem 7, Cauchy first theorem on limit. Cauchy's first theorem on limits. What is Cauchy's first theorem on limits? What is the statement? Let Sn be a sequence, and which is Sn is greater than 0 for all n belongs to n, and limit Sn exists, limit Sn is L, then limit n tending to infinite S1 plus S2 plus and so on Sn upon n is also equal to n. If limit Sn is L, then n tending to infinite S1 plus S2 plus S3 and so on Sn over n is also L, and it's the Cauchy first theorem on limit. So according on this theorem we take an example how to prove this result. So we take an example, and the example show that limit n tending to infinite 1 upon square root n square plus 1 plus 1 upon square root n square plus 2 and so on 1 upon square root n square plus n, this is equal to 1. We prove this result. This limit Sn is 1. How to prove this result? So solution. According to the question, it is just like, suppose this is S1, S2, S3, but in the Cauchy first theorem all the terms contain upon n, so we can write S1 plus S2 plus S3 Sn upon n, but here it is not, so we can write this result Sn is in the way 1 upon n and n upon under root n square plus 1 plus n upon square root n square plus 2, because when we take common n, then n and n cancel, and this is the same result 1 upon n square plus 1. So we can write as this form and so on n upon square root n square plus n. Now how to calculate? So this is the form of that. So it is clear कि here S1 is, what is S1? According to S1 is n upon n square plus 1 square root. And what is S2? S2 is n upon n square plus 2 and so on, and Sn is n upon square root n square plus n. Now we calculate limit Sn, because with the Cauchy theorem we find all the terms are positive, so here all the terms are positive for all n belongs to n, and calculate limit Sn. So limit n tending to infinite, Sn is n upon square root n square plus n. So take n square is common, limit n tending to infinite n, and this is 1 plus 1 upon n, n upon n square is common, so 1 upon n, and here n say n cancel, and taking limit. So we get the result n tending to infinite is 1 upon square root 1 plus 1 upon infinite. 1 upon infinite is 0, so that is 1 upon square root of 1 is 1, so that result is 1. Then we can say limit Sn is equal to 1. If limit Sn is 1, then and that is the form. So by the Cauchy first theorem, if limit Sn is 1, then limit n tending to infinite S1 plus S2 plus and so on Sn upon n is also 1. So that is the result. Okay, this S1 plus S2, this is that form of the condition. So S1 plus S2 plus S3, and this is also here. This is Sn, and that is the another name. We can say another condition. So we can write this is Sn, or we can say An, because the name is same, so confusion is that. So that's why we change the name, and the name is just like we take An, another sequence An, and that term is Sn. Okay. Now we go for the another theorem, Cauchy second theorem on limits. The 7 number theorem, and that is 8 number. Cauchy second theorem on limits. What is Cauchy's second theorem on limits? So let Sn be a sequence and if Sn be a sequence such that limit Sn is equal to L and all the terms are positive, Sn is greater than 0 for all n belongs to n, then limit S1 into S2 and tending to infinite, S1 into S2 into S3 and so on Sn is whole power 1 by n. This is also n, and that is the another theorem, and this theorem is called Cauchy's second theorem on limits. So we take an example on that theorem. So we take an example on that theorem. Show that limit n tending to infinite 2 upon 1 is whole power 1, 3 upon 2 whole power 2, 4 upon 3 whole power 3 and so on n plus 1 upon n whole power n and the whole power 1 by n, and that is equal to e. So that this result. So we can understand that all the terms are product on that way. So it is a form of S1, S2, S3. We can understand, and we can understand that in this question we have to apply the Cauchy's second theorem on limits. So how to apply? Check. This is S1. Here S1 is, this is 2 upon 1 whole power 1. And what is S2? By the Cauchy theorem, 3 upon 2 whole power 2. S3, 4 upon 3 whole power 3 and so on. And what is Sn? Sn is n plus 1 upon n whole power. Because 1 by n is here and 1 by n is here, so we can understand we have to apply this theorem on that types of question. S1, S2, S3 and Sn. So by the Cauchy second theorem, we have to calculate all the terms are greater than. So here Sn is greater than 0 for all n belongs to n. And calculate limit Sn. So what is the value of the limit Sn? Limit n tending to infinite. Sn is n plus 1 upon n whole power n. So the result limit n tending to infinite n divide. So 1 plus 1 upon n whole power n. And we know that the result n 1 plus n upon this is e. And the 12th, that result is e. So that is e. And by the Cauchy second theorem on limit, it is clear that limit n tending to infinite s1 into s2 into sn, s1, s2, s3, sn is whole power 1 by n. This is also L, and here L is just like E, so that is E, and that is the result. So we can say, okay, this question can be solved by the Cauchy second theorem on limits. So now we go for the another theorem. And the next theorem is Cauchy formula on limits. Cauchy formula on limits. What is the Cauchy formula on limits? So in this theorem, let Sn be any sequence such that and Sn is greater than 0 for all positive sequence, for all n belongs to n. Then if limit Sn whole power 1 by n, Sn की whole power 1 by n, not S1, S2, S3, Sn whole power 1 by n and n tending to infinite is equal to limit n tending to infinite Sn over Sn minus 1, or we can write that result is limit n tending to infinite. If we replace n is by n plus 1, so we can write n plus 1 upon Sn. Both are the same result. So limit n tending to infinite Sn whole power 1 by n is equal to limit n tending to infinite Sn plus 1 upon Sn. And that is the most important result of Cauchy formula on limits. So we use this formula, and how to solve this? So we take an example. Suppose limit n tending to infinite n raised to the power 1 by n. N raised to the power 1 by n is 1. Prove that n raised to the power 1 by n is n 1. How to prove this result? Show that. Most important result. So we go for the solution of this result. Here in this question we have to understand that this is the form of Sn whole power 1 by n, and so on comparing that result, limit n tending to infinite Sn whole power 1 by n, So it is clear on compare this by limit n tending to infinite n raised to the power 1 by n. On comparing, here Sn is, according Sn is n, and according to that this we have to calculate Sn plus 1 upon Sn. How to Sn plus 1? Sn plus 1 is replace n by n plus 1, so we can write n plus 1 upon n. Now we calculate the limit n tending to infinite Sn plus 1 upon Sn. So this is limit n tending to infinite, operate limit n plus 1 upon n. So divided by n, so limit n tending to infinite, this is 1 plus 1 upon n. Taking limit, this is 1 plus 1 upon infinite is 0. Taking limit, and 1 upon infinite is 0, so that's why this is goes to 1. So it is clear that limit n tending to infinite 1 Sn plus 1 upon Sn is 1. So it is clear by the Cauchy formula, Cauchy formula on limit, it is clear that limit n tending to infinite Sn whole power 1 by n is equal to limit n tending to infinite Sn plus 1 upon Sn, and that is result, and that this is 1. So it is clear that this is the result of this theorem. So by the Cauchy theorem, limit n tending to infinite Sn whole power 1 by n equal to Sn, limit n tending to infinite Sn plus 1 upon Sn is equal to 1. So that is the result of this theorem. Thank you.